Welcome to our webinar Selectivity in Line Protection. These sessions are made for those who start working or who are new in the field of protection and where a solid understanding of relay protection for distribution and transmission grids is essential. My name is Gerd Einsiedler and I'm happy to guide you through this second session of the webinar. Some of you might already know me. I have been working in protection and automation for nearly 30 years. Since September 2023, I'm part of Siemens Power Academy in Nuremberg as certified trainer for protection. And today I'm introducing you to Selectivity in Line Protection lectures with the topic How Selectivity Works in Distance Protection. And since we receive one question rather often, yes, we will record the webinar and make the recording and the slides available to all registered participants. If you already joined one of our last webinars, you already know the Q&A field in this application. Please type in your questions to the presenter in the question field. We will answer your questions during the dedicated Q&A session after the series on 21st of June. In addition to me reading aloud your questions, you could also chat with our experts in the background. Please be aware of the following limitation. The chat is available in live mode only. Q&A questions will be answered via email if not managed during the live session. And just in case you are in full screen mode, press Escape to see the Q&A and chat box. And now let me introduce our expert, Professor Dr. Siegfried Lemmer. Siegfried Lemmer graduated and received his PhD at RWTH Aachen University. He joined Siemens in 1986. For many years he was head of the product lifecycle management for protection, where he was deeply involved in the design of the C-Protect 4 and C-Protect 5 relay families. Within a master course of power engineering at Brandenburg University of Technology, Cottbus-Senftenberg, he presented lectures about protection for nearly 2 decades. In 2016, he retired from Siemens but continued his university lectures. Siegfried, and now we are curious to learn more about the selectivity of protection. The stage is yours.
This video is on selectivity for distance protection. This will be a little bit a longer thing. This shows the topics I would like to discuss. First of all, main point of a distance protection, detection of faults on the protected line. We will then look at higher zones, at the pickup zones, and then finally at 2 dedicated topics which also affect the selectivity, the influence of fault resistances and the intermediate infeeds. So let's start with detection of faults on the protected line. Remember, the principle of distance protection is illustrated here again on this slide. In the upper diagram you see a part of a network. This network is a meshed system. I show here only one protection relay protecting this upper line. This protection relay measures permanently the impedance into the line, and if there is a fault on the line, it measures the impedance of the piece of line from the relay to the fault. That means if it measures this low impedance, it knows there is a fault on the line. If there is a fault on the next line, it will also see this fault, but it will measure an impedance which is a bit higher, and from that comparison of the measured impedance with the impedance of the line, it can decide is the fault on the line or not. That means basically the distance protection principle will lead to selectivity. So from the measurement principle, it is selective, but there is a but, and to understand this but, we have to go a little bit into the details. First of all, I would like to look a little bit more into this measurement. What does this measurement mean? As a first approach, I make a very simple replica of the line. I just represent the line by resistance. I know that's not true, but to understand the principle, it's a good way. That means we assume we have a line. Beyond the line, we have a rest of a system, and we replace that by just an equivalent resistor, in this picture called the load resistor. And on the beginning of the line, we measure the voltage and the current and can calculate the impedance. And in normal operation, if we measure the voltage and the current and divide the voltage by the current, we measure a pretty high resistance of the line plus the load resistance, which is an equivalent for the rest of the system behind that. It's a pretty high value. If now we have a short circuit on the line, it looks like this. That means we make a short circuit from somewhere of the line to ground. Then we measure a reduced voltage, a high short circuit current, and the result, voltage divided by current, is a percentage X of the line resistance. And if we have a fault on the next line, a short circuit on the next line, it looks like this. We have a circuit where we measure the resistance of our own line, a part of resistance of the next line. That means also a low value, but higher than in the first case where we have a fault on the line. That means if we compare the measured resistance with the known resistance of the line, we could make the decision, is the fault on the line or not. So in reality, it's unfortunately a bit more complex. We have a three-phase system, and impedances are always defined in loops. And if we have three phases, we can define in total 6 loops. We can define the impedance between phase 1 to ground, phase 2 to ground, phase 3 to ground. And we can also measure the impedances between the phases, between phase 1 to phase 2, phase 2 to phase 3, and phase 3 to phase 1. That means a normal protection relay has to deal with all these 6 impedances in parallel. That's a bit of workload for the relay, but in most cases we don't have to consider this in the following slides. Normally modern relays always handle these 6 loops in parallel. You may still have some relays in operation which are called switched relays. In older technologies like electronic relays or electromechanical relays, or also in the early days of digital relays, people were using switched relays, and these relays were only measuring one loop. That means they had to decide in the beginning which loop to measure. But nowadays, you can say all modern relays measure all 6 loops in parallel. That is one thing we have to take into account. Another thing is we are dealing with AC. That means we cannot talk about resistances. We represent impedances by complex values. That means an impedance consists of a resistive part and a reactive part, and we show that in such a diagram where the resistive part is the horizontal axis and the reactive part is the vertical axis. That means the impedance of a line can be represented in this form as this red arrow, just indicating that it has the line resistance RL and the line reactance XL, and this direction where the arrow is on the so-called line characteristic. The angle of this line characteristic is for overhead lines in this area as shown in the diagram. You can say 80 degrees, 85 degrees, or for extra high voltage even a bit higher. For cables it's a bit more flat. That means there the resistive part is higher. So now what is going to happen if the distance relay measures the impedance all the day long into the line? If we have normal operation, the distance relay also measures a complex value with a resistive and a reactive part. If we have real power flow on the line, the impedance we measure is mainly a resistive impedance, and it is somewhere here where I indicate normal operation. The thing, it's important to understand this diagram. If you have very low load on the line, you move to the right. You move outside the diagram. If the load increases, you approach the diagram. Because impedance is voltage divided by current. If the current increases, the impedance decreases, and then you move into the diagram. If you have a fault on the line, short circuit, you measure an impedance which is, in this case, the middle of the line, which is somewhere here. That means you measure an impedance which is somewhere on our red arrow. If you would have a short circuit at the very beginning of the line, you would measure a point in the origin. If you would have a short circuit at the end of the line, you would measure an impedance which is at the end of this arrow. And if you have a fault with a fault resistance, that is a thing which also can happen. If you have a phase to ground fault somewhere on the tower, we have a lightning arc with a fault resistance, we have a tower resistance, then you move out to the right. That means fault without fault resistance is on a certain location on the red arrow. If you have fault resistance, you move to the right. You move to the right, the bigger the fault resistance is. And if you have a fault on the next line, you are somewhere there. That means, as a result of this discussion, we don't want to draw nice diagrams. What we want to do is we want to make the decision, is the fault on our line or not? And what can we take? We see the resistive part of the measured impedance is influenced by the fault resistance. And it can be anything. It can be zero, it can be a high fault resistance. But what we also see, the reactance is not influenced. That means we can take the measured reactive part, the reactance to the fault, as a criterion, is the fault on our line or not. That means the fault distance can be estimated from the measured reactance. We measure the complex impedance, split it into resistive and reactive part, and then we take the reactance as a criterion where the fault is. We compare that with the reactance of the line, and if it is lower than the reactance of the line, we know the fault is on the line. And that is the idea of the first zone of a distance protection relay. That means we take again this complex plane, and then we define a certain area in the complex plane, and if we detect a fault in this area, we say, okay, the fault is on the line. And in the first step we would say, okay, as we just discussed, the upper limit is the line reactance. That means we must, if we want to set a distance relay, We ask our network planning people, what is the total reactance of our line? And then we say, okay, that is our horizontal limit. Then, of course, in order to have a complete area, we must also define on the right side somehow a limitation. And that is already a bit a tricky thing, because we must now decide what amount of fault resistance do we want to catch. So if we make this pretty narrow, that would mean if we have a significant fault resistance, we would measure something outside the zone and would not trip on that. If we make it very big, we have the risk that with the load flow, remember, with the load, increasing load, we move into our diagram. That means we must be careful with the right side of this thing, that we don't go too far. Then we would be very sensitive. We would be able to catch high resistive faults. But in a strong load situation, the measured point would move in and we would trip on load. That is not good. So that is always a discussion, this resistance reserve, how to set it in distance relay. And we will talk about that a bit more at the end of this video. And then to make this area complete, normally we would say, okay, we could limit it to the first quadrant. For some reasons, it's normally widened up a bit. That means the first zone looks like this. And we would say, okay, this is our setting. We make a reactive setting, 100% of the line reactance. The resistive setting, we calculate it somehow from fault resistance as we expect. And if we find a fault, a short circuit, or if we measure an impedance inside this characteristic, we would trip. So the question is, will that work? It looks nice, selective. As soon as the short circuit is a little bit beyond this XL on the next line, it will not trip. The question is, does that work? And you can imagine if I ask the question like that, the answer is no, it does not work. Why will such a setting cause problem? It will cause problem because the impedance measurement is subject to measurement errors. And in distance protection, you have quite a number of measurement errors. You measure the currents and voltages through current transformer and voltage transformer. That means you have a measurement error in the current transformer, you have a measurement error in the voltage transformer. The relays have, of course, also a limited accuracy. Then you have other disturbing effects which also influence your measurements. If you want to measure phase-to-ground faults, you must know the zero sequence quantity of the line. This is also not very much known. And the result of this discussion is that this horizontal line is not really a sharp line. This horizontal line looks more or less like this. Depending on the measurement error in which directions they go, it can be a bit higher or a bit lower. And the same refers to the right limitation. And what is the result of that? The result of that is if you have a fault just beyond your line, at the beginning of the next line, it can be seen inside the characteristic with our setting because of these measurement errors. Or the result can also be if you have a fault just on the line but pretty much near the end, the relay measurement says, no, it's outside. I don't see it in the zone. And that is a principal problem in distance protection, that you have to live with this unsharp limitation. And one thing which bother people most in this context, you may cause wrong trips. Because a short circuit on the very beginning of the next line may be seen inside the zone with these settings. That means this approach of making the horizontal limit to 100% of the line reactance doesn't work. It may lead to wrong trips, and that is why it is normally not used. So what can you do as an alternative? We start with the same thing. We have here our line characteristic. We have the line impedance consisting of the reactive part XL, the resistive part RL. And now we make our limit a bit deeper, a bit lower, to avoid these wrong trips. And what you typically do to cover possible measurement errors is making some 10 to 20% lower. That means you make a setting of this horizontal limit not to 100% of the line reactance, but for instance to 85% of the line reactance. Then the same story, right limitation for the fault resistance, and to make this area complete also that limitations. That means we have a setting that the X value is 80 to 90% of the line reactance. And that is a standard value which is normally applied in distance protection. That avoids wrong tripping with faults on the next line, even with measurement errors. But of course it has a disadvantage. The disadvantage is, you can imagine here, at the end of the line, if you say, okay, we have no measurement errors, at the end of the line you have a certain part of the line where a short circuit will not be seen in the first zone, but as you can say here, at least you avoid wrong trips. And that is the important thing. You avoid, with this setting, and this is a standard way of setting distance relays, you avoid wrong trips, but we must keep in mind, by using these settings, we have a problem that short circuits near the end of the lines will not be seen by the relay and will not be tripped fast. That means we also have to find a solution for that. Up to now, we looked only at one relay. In real life, of course, every line has two ends. That means if there is a fault on the line, the measurement is from both sides. And I would like to illustrate that a little bit using a simulation. In this simulation I prepared, you can see the measurement of relays on both sides of the line in parallel. You see here on the top the line. In this case it's a 200 kilometer line, and in the bottom part you see the first zone of the two protection relays on both sides. You see they have identical settings because they are protecting the same line. We have an X setting of 60%, so that is the 85% of the line reactance. And in this case we have an R setting of 20 ohms, as can be seen here on the bottom. We have no pre-fault load. You see here the pre-fault load is 0 in this case. We will discuss the load influence a little bit later. And now I would like to simulate a fault somewhere on the middle of the line. 50%, we make a face-to-face fault. And now you see here what both relays measure. In this case, the fault is on the middle. The relay measure the same. If the fault is near the left side, then the left side relay, of course, will see the fault closer. The right side relay will see the fault a bit further away. And if we measure or if we have a fault 80, 81, you see here fault at 85% without any measurement errors. So this simulation runs without measurement errors. Then we are exactly at the limit. That means if we have a fault at maybe 90% of the line, then the left relay will see the fault outside the first zone if we have no measurement errors. If we take into account the measurement errors, it may see it inside or it may see outside, depending on in which direction the measurement errors go. And we know Murphy's law, which says that the measurement errors always go into the wrong side. That means we have to keep that in mind, that we have, by this setting of 85%, we have the problem that we have at the end of a line a certain part where at least from one side the fault is not tripped. The other side, what you can see here, in this case the right relay of course would trip the fault pretty fast. And only in the center, that means from 15, the same problem of course occurs also from the other side. That means if the fault is here in the area of very much near the left side, between 0 and 15% of the line, then the right side will not see the fault and will not trip fast. That means only in the center part from 15 to 85, both relays will trip the fault. What you can also see, if you add some fault resistance, it moves out a little bit to the right, and we will discuss that a little bit later. So that was a look into the simulation. Up to now we had a look at quadrilateral characteristic. That means we have a characteristic where we can make the reactive and the resistive setting independently. If you look into applications worldwide, there are also a lot of relays in operation which have a completely different characteristic. They have a circular characteristic, so-called Mohs circles. What is behind that? Also there, like with the inverse time curve, it comes from traditional measurement technology. That means in the early days of distance protection, there were electromechanical devices, and having such rectangular characteristics or quadrilateral characteristics was not possible with electromechanical devices. So based on the possibilities in electromechanical devices, we had circular characteristics, and in many countries they are still in use. I think they have a little bit the disadvantage that you cannot set reactance and resistance independently. But the situation you often have is you have many of relays with circular characteristic in operation. You want to replace relays. And if you are happy with the behavior of your characteristic, you have calculated already all the settings for this circular characteristic, you don't like to have suddenly relays with quadrilateral characteristics, even if they have some advantages. If you are happy with circles, you ask, I want to replace relays, old relays by new relays, but I want to take the same setting values. And for that reason, we also have the option, instead of using this circular characteristic, to use so-called Mohs characteristic. The idea behind that is the same. You have this circular characteristic. The setting principle is also the same. That means this circle is also a bit an unsharp thing due to measurement errors, because you have to deal with the same measurement errors. And that means you also have to do this reduced setting of 80 or 85%. and you make then a timer setting. That means all the other ideas I would like to discuss later on are also applicable if we have this type of the characteristic. Now let's look into higher zones. Up to now we discussed zone 1. Zone 1 reacts on most faults of the line, but we must have in mind there is a certain part at the beginning and at the end of the line which are not seen in the first zone, depending on the measurement errors. And that's one reason why we have higher zones. And if you look into a manual of a distance relays, you will see many zones. So you might ask your question, why do distance relay have more zones? One possible answer would be to react on faults at the end of the protected line. That is a thing I already discussed. Another option it could be a backup for the next line. The reason could be we want to confuse the protection engineer. Or a last thing, these things are required for other functions like teleprotection, auto reclose and whatever. And you can imagine I have 4 options here. 3 of them are valid and 1 is not valid, but I also would like to make or to say a few words on that. We will discuss a bit more in detail how to use higher zones to react on faults at the end of the line. We will also discuss the backup situation. But what about are they used to confuse the protection in the? Some people sometimes have the impression, and I had many discussions on the number of parameters and setting values and functions we have in the protection relays. Yes, protection relays is, or the distance protection function is a complicated function. You need, just based on the principle, you need a lot of parameters to do that properly. And then you have worldwide a lot of flavors and different special applications which sometimes need an additional timer here, an additional corner in the characteristic there. And that makes the thing complicated, and all protection manufacturers have to make up their mind how can you deal with the amount of parameters. And additionally, we must also have in mind we have a lot of integrated function in a modern protection relay, and that makes it complicated. And of course, we had to think a lot about that. We had a lot of discussions about how can we make it easier for the user. And the result cannot be that we make user-specific protection devices, user-specific software, where the user does only see the functions he needs and the parameters he needs, because that would end up in a mass of different software. That is not manageable. So what we did is we invested a lot of brain in structure the software in a way that you do not see things you don't need, that you can do the engineering, for instance, and that is a very important step in this context, that you can do the engineering based on templates. That means in your company, you can make a template which is already very similar to that what you end up, so that you don't have to look at all the other things. But nevertheless, the manual has still to cover the full set of parameters and possibilities of the relay. And that is the reason why the manuals of protection relays, especially of line protection relays, are pretty thick. It's not to confuse the protection engineers, it's just the difference and the variations of functions which are used all over the world to do the protection function. Now let's look at the first point. How can we react at faults at the end of the protected line? This shows again our line. In this case, it's a 100 kilometer line. And this indicates now the reach of the first zone. Remember, if we again forget about measurement errors, if we assume we have no measurement errors, the first zone of the left relay would look or would cover 85% of the line. The same applies to the relay on the right side. It would also cover 85% of the line. That means on both sides we have this remaining 15% that are exactly 15% if we have no measurement errors. It can be more or less than 15%. So now what we can do is to compensate this problem. We add a zone 2. A zone 2 is just a second zone, which is a bit wider. It looks a bit wider into the relay. And that should be wide enough so that we are sure that the remaining 15% are covered, even if we have measurement errors. And that means it must be at least 15% beyond the end of the line. If we do that from both sides, of course, that would mean if there is a fault in this remaining 15%, this fault will definitely be tripped also from the left side, unfortunately with a little bit of delay, but it will be tripped. And that is one purpose of zone 2, delayed trip. In extra high voltage, delayed trip is not acceptable. That means you have to do some more things to bring this time down. That is where teleprotection comes in, but that's a different topic. So here we are at least sure we see this fault in zone 2 and we will trip on that. So that was the purpose, to cover the remaining 18%. But we also have to think about the backup. Remember, we always have to make up our mind. If we have a fault somewhere and the relay which should trip does not trip, what is going to happen then? And distance protection has the nice feature that the remote backup is always there, and I can show that in this example. We again here have our 100 kilometer line. Now I look also into the next line, which is a 70 kilometer line in this case. So on the 100 kilometer line, that is the first zone, 85%. And the same is also there on the right line, on the 70 kilometer line. Also there we make a setting of 85%. So now we look at zone 2. If we remember the setting I just described on the previous slide, it looks a little bit into the following line. That means if we have no measurement errors, it would already be a backup for the first 15% of the 70 kilometer line. And at that point, you could have the idea, oh, why don't we extend zone 2? Let's make zone 2 longer, then we have backup for a higher part of the line. And that is what you normally do with the zone 2. You make zone 2 long enough so that it covers as much as possible of the next line as a backup. Also there you must be careful. You must keep a certain distance to the end of the zone 1 of this line, as indicated there on the right hand side. Otherwise you will get conflicts with selectivity. But at least with that you can do a backup of a significant percentage of that line. That means the rule for zone 2 is, as indicated here, at least 15% higher than the reactance of the line, and it should be, like indicated in that equation, it must keep a certain distance from the end of zone 1 of the next line. And the problem, which is not visible in this slide, unfortunately, is you often, in a meshed system, you often have not only one next line, it can be several lines there. And there you have to take the smallest next line, or the next line with the smallest resistance, or reactance, sorry. And you can imagine, if you want to do that calculation for a bigger system, again, doing that by hand is a bit a tricky thing. And for that reason, also this type of grading, calculating of the zones, is normally done by computer programs. The program Syncal I mentioned is able to do the grading of a distance relay. And then you end up, for instance, in such grading diagrams as indicated here on the left side. You consider one line, that is this line L1, and here I indicate several next lines. That means all the lines going away from the next substations. They have different length, and the grading must take into account the length of the shortest following line, and that is in case this the L4, and you see this yellow arrow there, which indicates that with the reach of zone 2 of our line 1, we must keep a certain distance to the zone 1 end of line L4. And this can be continued not only to zone 2, you can also define a zone 3 and whatever you need in your application. There are different numbers of zones in use. So you end up in such a diagram. Sometimes you also have applications where you, for any special reason, want to look a little bit reverse. That means instead of looking only forward into your line, you make one zone which looks reverse. That is typically also a backup application. That means in addition to the zone size, you also have a parameter defining whether a zone looks into a forward direction or a reverse direction. And then, if you look into a manual of a protection relay, you often find in the description a so-called pickup zone. What is that? Actually, the pickup zone is the outer zone. That means, depending on how many zones you have, it's the biggest zone. In some relays, it has different name. It's really called pickup zone, but sometimes it's just the outer zone. And this pickup zone requires particular attention, because you must be careful to define the size of this pickup zone. And this pickup zone defines two things. You should be aware if the impedance measurement with heavy load, remember, with heavy load you are approaching, the measured impedance is approaching our characteristic. And if you are in a critical situation, you suddenly may move into the characteristic and then you will trip. You normally have delay times, so all zones have delay times. That means the pickup zone typically has the highest delay time. So it may have a delay time of a second. But if it moves in a second, the control center is not able to react on that. You will trip. That means if you define your pickup zone, you must be pretty sure that you don't run into the pickup zone in normal operation. That means make it small. The other thing is you can only detect faults inside the pickup zone. That means if a fault has a fault resistance, remember it moves to the right. So it moves in that direction. That means if you make your pickup zone too small, you have the risk that you don't see some faults. You may have resistive faults that you don't see. And that makes the setting of the pickup zone a bit critical. You must investigate heavy load situations, and you must make the setting, the zone, small enough that the protection does not pick up. And heavy load situations, the critical thing, for instance, is you have a system, maybe with a heavy load transfer from one area of the system to the other. That means the lines connecting these two parts of the systems are heavily loaded. And now you have a thunderstorm and one line has a short circuit, it trips. In case of a short circuit, we have to trip the line. What's now going to happen? The other lines connecting these two parts of the systems have to take over, because one line is shortly out of service because of the trip. The other lines have to take over. That means they are overloaded for a short time. And if at that moment you run by this overload into the characteristic and you will trip, that means you lose even one more line, and then you end up in a cascading outage, and that may end up in a blackout situation. So that is a very thing where you have really do investigations. You have to find out really all critical situations which may occur, not today, but also not only today, but also in future. No, because you want to to define the settings now, and they should also be valid in a couple of years. And the other thing you also have to investigate is you have to investigate faults with low short circuit currents. That means you have to take into account fault resistances, and you also have to take into account backup cases. And also there, detailed calculations are necessary. Fault resistance, what you normally do there is the majority of faults, of single phase to ground faults, are in overhead lines, are lightning arcs on towers. That means there you can do an estimation. What is the resistance of the lightning arc? And then the current goes down into the tower and via the earth wire also to the other towers. You can make an estimation of the short circuit of the resistance in these paths, and from that you can derive your settings of the pickup zone and of the other zones. But of course you can theoretically, you can also have something else. In a distribution system there could be a risk that a tree falls into the line. In transmission it's not so critical. But of course you could theoretically also have a broken wire, and then a wire in a sub-transmission system, for instance, a wire falls down to earth, and then you have a significant, if you have a rocky area or somewhere in the desert, you can have pretty high fault resistances there. And that is the point where you have to make up your mind. Are you able to catch these types of fault with distance protection? That means in this conflict, can you make the pickup area big enough to catch these faults? Or do you have to say, okay, distance protection stops here. For these special types of fault, I have to think about special earth fault protection. Okay, that was a look at the settings. This diagram shows a little bit the structure of a modern protection relay. So on the left-hand side, you see we measure the currents and the voltages. And then we measure in parallel 6 impedances. So you see here the measurement blocks for the 3 face-to-face and 3 face-to-ground impedances. We compare that with the characteristic. Pick-up function controls a little bit the whole story, gives some signals if we detect something. And then with the whole thing we run into a trip logic. There we have the timers. Timers start as soon as an impedance runs into a zone. We will start the timer of this zone. And if we decide to make a trip command, this logic will issue a trip. And what you also see here is we have 2 different options for a trip. So the standard thing is if we trip all 3 poles of a breaker. But remember, in overhead lines we often have auto reclose active. And in auto reclose we have in many applications the concept of doing single pole auto reclose. And that means we don't give a trip command for all 3 poles of the breaker. We see what type of fault do we have. Phase 2 to ground fault, and then you give a trip command only to the phase 2 of the breaker. That means protection relays which are able to do single pole auto reclose have, in addition to the 3-pole trip, also single pole trip commands. This slide shows the characteristic we have actually available in our CProtect 5 distance relays with all the different features you have. You see the outer zone is, in this case, not rectangular. It's a little bit tilt in a parallelogram form. Inner zone is shaded in gray, the zone 1. Also there we have the option for some special applications. Again, another parameter to tilt the top a little bit because it's needed for some applications. And what is also visible here is these load cutouts on both sides, shaded here in gray. And these load cutouts are or have been designed to allow, on one hand, that the load point or that the measured impedance can move somehow into the characteristic, can approach the characteristic. That means in that area where the load typically is around the resistive axis, there we cut out a little bit of the characteristic. That means if the measured point approaches the characteristic, moves in, but still within this gray area, then we will not pick up. That's called load cut out. But on the other hand, if we have a short circuit, we are somewhere in the upper right corner of the relay, we can still react on that. And that means this conflict between shrinking the pickup zone to avoid load problems, making it big to catch all the faults, that conflict can be solved a little bit by making this load cutout. Of course, again, you have a couple of more parameters which are used to define this load cutout and which are, of course, not used in all applications. And the same is also possible for the Mohs circle. Also there we offer the possibility to make such a load cutout. So in the final part I would like to talk a bit about fault resistances, because dealing with fault resistance is unfortunately a topic you are often facing if you deal with distance protection. Because if you do the zone settings, you have to think about fault resistances, and for that reason it makes sense to look at that a little bit more in detail. Let's first of all assume one simple line. You see here a diagram On the left-hand side, we have a protection relay. We have a short circuit with a fault resistance. And on the right-hand side, we assume the rest of the line. And in the first step, we assume there is no infeed from the other side. Then it is pretty simple. We can write down the equations of this circuit. The impedance we can calculate by dividing the voltage by the current is the impedance of this piece of the line between relay and the fault plus the fault resistance. And if we draw that into our diagram, we see here this piece of line, resistive and reactive part shown as an arrow, and the fault resistance has no reactive part because it's only a resistance, there's not a reactance which has to be considered. So at the end we measure the sum of these two things. That means this is the operating point we measure there. If we now have, as it is the normal situation in a mesh system, if we have infeed also from the other side, we get an equivalent circuit like that. That means we feed now the fault from the left side and also from the right side. And that means the right side now drives a short circuit current through the fault resistance. This gives a voltage, an additional voltage drop through the fault resistance, which is seen by the left relay. That means the current from the right side influences the measurement on the left relay. You can easily write this down in equation. I don't want to go through all this equation, but the result is you get this additional value here. That means instead of measuring, as indicated in this plot now, the piece of line plus the fault resistance, you measure an additional part, which is here in this red box. It is proportional to the fault resistance, but multiplied by AB divided by IA, sorry. That means if the current from both sides are the same, this ratio would be 1, then you would measure just double the fault resistance. And depending on the ratio, it can be higher or lower. And that is how a normal distance algorithm reacts. That means if we are in a meshed system where current comes from both sides, and we measure, we have for instance a setting of 20 ohms, and we have a fault resistance of 10 ohms, we can even, based on this effect, move out of the characteristic. And that is a thing which has to be taken into account in the settings. That means if you look into the setting recommendations in our manuals, you will find a strange formula where you need the current from the other side. And that is the reason behind that. And what you can also see from this simple calculation here is what is the worst case. The worst case is if this ratio IB over IA becomes pretty high. And that is a situation where the majority of the short circuit current comes from the other side. That means if our left protection relay has a weak infeed behind it and you have a strong infeed on the other side, then this ratio becomes pretty high, and then you may move out of the characteristic. And that's only one part of the story. It goes even further. These quantities here are complex quantities. That means the ratio can become complex if the phase angles of the currents from both sides are different. And if this ratio becomes complex, you do not only have to add a horizontal error, it can turn the whole thing a little bit. And that means you can even, if you are close to the limit, you go to the right and you can even go up here and can leave the characteristic over there. So for that reason, that has to be taken into account. And also this we can discuss a little bit more using my simulation. Yeah, I'd now like to show these discussed cases again in my simulation, just to repeat and you see what's going to happen. So we see here again the line with a fault on the middle of the line. In this case, I have set the infeed from the right side to nearly zero. That means we have no infeed from, no current, short circuit current coming from the right side. And that is why the red dot on the right relay side is missing. Because if the relay doesn't see current, it cannot do the measurement. Every distance relay needs a certain minimum short circuit current to do the measurement. Again, that is a setting value which has normally a reasonable preset, so you don't have to change it. So now let's see what happens if we add fault resistance. We move to the right. Here this is 10 ohms. And what you now see is if we are at 20 ohms, 20 ohms, you are nearly at the limit. We made a setting of 20 ohms. We have infeed from one side and we exactly see what we expect. Now the next step is, let's reactivate the infeed from the other side. So I will now take the resistance back. I will now add or reactivate the infeed from the other side. Now we have the situation, the fault is again on the middle of the line, but we have current coming from both sides. And as the infeeds on both sides are more or less identical, we are on the middle of the line. We have the same short circuit current from both sides. That means this ratios IB over IA I showed on my slides is 1. And that means what we measure is, the impedance we measure is the impedance of the piece of line, 50% of the line, plus fault resistance, plus IB over II multiplied by fault resistance, which is 1. That means we measure 2 times the fault resistance. And we can see that here as a result. We move now much faster to the end. That means already with 10 ohms, we are now reaching the limit. That means we have a setting of 20 ohms and we are approaching the limit already with 10 ohms due to the short circuit current coming from the other side. But, and that is the good thing, we still move horizontally. You can show that a little bit better by activate this tracing. So you see here, with increasing fault resistance, the reactance measurement is not influenced. That means we just have to look at the reactance limit. We must be aware in this setting and at this location we can only detect faults up to a fault resistance of 10 ohms in the first zone. A fault with a higher fault resistance would probably be seen in a higher zone. Okay, now we can make the fault closer to the limit. Maybe we have a fault here. And if we Now do the same thing. We see we move still horizontally, but what we see now is, let us say we take 10 ohms. Here the left relay is already outside the characteristic, whereas the right relay is still inside the characteristic. Why is this? This is because, remember, what we measure is impedance of the part of line plus fault resistance plus IB divided by IA multiplied with the fault resistance. If we have a fault at that point, for the left relay, the current it sees is lower than from the other side. The fault is very close to the right side. That means the majority of the fault current comes from the right side. Only a smaller part comes from the left side. That means the ratio IB over IA becomes much bigger than 1. And that is why the measurement of the left relay moves faster to the right as the measurement of the relay on the right side. And now we consider the worst case. We consider the case where the phase angles from both sides are different. What is the point behind that? Under which conditions can the phase angles of the short circuit current be different? They are different if the voltage angles are different from both sides. And if the voltage angles are different, without a short circuit, we have a load flow. That means a power flow on the line requires that the voltage phase angles are different. And that means if we have a power flow on the line before the short circuit occurs, that means the voltage phase angles are different. If the voltage phase angles are different, during the short circuit, the current phase angles are different, and that causes problems. That means there is a relation between pre-fault load flow and the movement of our impedance measurement. And I will also show that in the simulation by activating a pre-fault load flow. So now you see a situation where we have a pre-fault load flow. So you see it here in the drawing of the network. We have a pre-fault load flow of 400 and something real power and also some reactive power flowing. And now look what happens if we increase the fault resistance. The measured points, look at the measurement on the left relay. It moves due to this effect not horizontally, but it moves up. If I activate tracing, it becomes a bit more visible. And we leave the characteristic already, make the tracing back. That means already here with 3 ohms fault resistance for this fault location, we would already be outside the characteristic. That means fault resistances in distance protection have impacts in 2 directions. On one hand, this movement to the right depends on the ratio of the current of both sides. That means we must consider that when doing the setting for the resistive reach. And if we have pre-fault load flow, we get this effect that the movement is no longer horizontal, but we move with a certain slope. Depending on the load flow direction, it goes either up or down. So you can see the left side moves up and the right side moves down a little bit. It depends on the direction of the load flow, and of course it also depends on the amount of load flow we have there. And that is of course a thing we would not like, because we have here in this case we had a fault at 82%, and with a few ohms we already move out of the characteristic. As I mentioned, that is the behavior of the standard distance algorithms. Theoretically, it is not possible to really take into account and to compensate the effect of the fault resistance completely. Because if you write down your equations, you have more unknowns than equations. So theoretically, there is no possibility to solve that properly. But you can do some approaches. And one thing we implemented and we really recommend is the so-called RMD method or reactance method, RMD method, in our protection relays. That means in our protection relays you have the possibility to activate either the conventional algorithms, as I showed up to now, or you can activate the RMD method, which then solves to a certain extent this problem. Unfortunately, you have to set again a few parameters. Sorry for that, but the algorithm requires that. And I can also show in the simulation what happens. I called it here reactance method. In the manuals you find RMD method. I have now activated this method. And what you see is if I do that, then although we have pre-fault load flow, the movement is horizontally. That means it really gives a better measurement in case of fault resistances and pre-fault load flow. And for that reason, and because it also has some other advantages, we highly recommend to activate that method in our protection relays. So that was a short look at the simulation. We will now continue with the slides again. So after this look into the simulation, I would like to do some concluding remarks on the issue of fault resistances. We saw that fault resistances in conjunction with pre-fault load can influence also the reactance measurement. That means they would move the measured impedance not only to the right, but also up or down. This can be avoided by activating the reactance method in a distance relay. So it reduces this influence. Theoretically, it cannot reduce it to zero, but for practical applications, it's okay. And besides that, it also has some other advantages. If we talk about how wide can we set the resistive reach of the zones, you think, yeah, let's set it very wide so we make the relay sensitive. We always have to think about load encroachment. That means we cannot make it as wide as we would like, because we always have to avoid that a load point, that during heavy load situation, a critical network situation where something happened but no short circuit, that we suddenly move into the characteristic and trip. And this load cutout can help us in this context. And important is that you do proper setting calculations for the resistive reach. And they are sometimes different, especially if you look into single phase to ground fault. They are different for the classical method and the RMD method. So please have a look into our setting examples in the manuals. But whatever we do there, we have some sensitivity limits. That means we can catch faults up to a certain fault resistance, and everything beyond that is not visible for the distance relay. And if we want to catch high resistive faults, we may have to activate separate earth faults functions which are tuned to detect these faults. Typically they are not so fast because there are no high currents involved in these cases, but you can then tune other principles a bit to detect these type of faults. And the last thing I would like to mention in the context of sensitivity with distance protection is also an important thing, is the role of intermediate infeed. And intermediate infeed is a thing which is only relevant for the backup case. That means the case where we measure into the next line, not into our own line, but we want to do the measurement beyond a substation into the next line, which is required normally for the backup case. And if we do that, we typically have the situation which is illustrated in this drawing. That means between the relay and the fault on the next line, we may have an infeed, because there is some other lines coming in there and they also have some short circuit current. And this infeed is called intermediate infeed. And that also disturbs our measurement, because it injects, in this case, this blue current, which flows then also through this part of the faulty line to the short circuit. It generates a voltage drop there across this line, and this voltage is seen by our relay and it influences the measurement. You can again set up equations as we did it for the faults with fault resistance. On the left hand side you see the equivalent diagram for the situation without intermediate infeed. So our relay measures the impedance of its own line plus the impedance of the part of the next line up to the fault. Then we assume a fault without fault resistance to keep it simple. And then we can calculate from that the impedance. We measure the impedance of our own line plus the impedance of the next line. If we do the same thing for this right situation with intermediate infeed, the equations change a little bit. And if you write down the equations, you again get this red dotted box with a ratio IB over IA. That means you see an additional impedance. That means the measurement gets a measurement error, it gets a higher value, and the value is IB over IA multiplied by this impedance of the line. That means, again there, if the intermediate infeed is nearly zero, IB over IA becomes zero, then you can forget it. But the critical case again is if the infeed behind you is relatively low, weak infeed, and the intermediate infeed is pretty strong, then that means IB over IA becomes a high factor, and that means you have a significant increase of the measured impedance. Now what does that mean? Imagine you have a setting of the zone 2 that looks into your next line as a backup case. And maybe you calculated the setting and you found out, okay, I cover maybe 70% of the next line in a backup. That's only relevant for backup, no? Because we are dealing with the next line. Now, due to this intermediate infeed, you measure a higher value. That means if there is really a fault at maybe 65%, you would expect a setting to 70, you have a fault at 65, you would expect it's inside my zone 2. But due to this intermediate effect, the measured impedance is much higher, so it's seen above 70%. The relay says, not in zone 2, I will not trip. That means the measured impedance is greater than it is in reality due to this effect, and that means the reach of the zone decreases. We do no longer cover 70%, but maybe only 60, 50, 40, depending on on this ratio. That means you think you have a backup, zone 2 has a backup for bigger percentage of the next line, but in reality, due to this intermediate infect, it's not the case. And that is where now zone 3 or even the pick-up zone comes in. You have to check at least the pick-up zone should cover also with intermediate infeed the whole next line, because otherwise you would not have a backup situation there. That means this effect of intermediate infeed has to be considered if you check whether a backup can be secured for every fault location in your system. And with that we are reaching the end. So that was a look into the selectivity for distance protection.
Thank you, Siegfried. That has been an interesting session with insights into the selectivity of protection. Dear auditorium, thanks a lot for your questions. We will answer these in the Q&A session on 21st of June. If questions come into your mind later, or you would like to go for more details, please visit our training platform at Siemens Power Academy. I'm sure you will find the right information and training. The access to the recording and the slides will be sent to all participants. Thank you very much for your active participation. It was a pleasure for me to guide you through the sessions on selectivity in line protection. And in this session, we learned how selectivity works in distance protection. I'm looking forward to meeting you soon in the next session of selectivity in line protection on June the 18th, which is focusing on how we can make the differential protection work selective and what does the application look like in line differential protection. Stay safe and sound, take care and goodbye.